بسم الله الرحمن الرحيم والصلاة والسلام على رسوله الأمين. كلية السلامة للعلوم والتكنولوجيا، قسم الهندسة الكهربائية، التخصص قدرة، الفرقة الخامسة، المقرر قدر 5107، الديناميكا الحرارية Thermodynamics. مرحب بكم في محاضرة هذا اليوم، وهذه هي المحاضرة رقم 4 بعنوان مخططات TSTS diagrams. Now, as we have explained before, diagrams play a very important role in the study of thermodynamics, and previously we have considered the PV diagram, the pressure volume diagram, and we have seen how we can make use of that diagram in order to obtain some of the properties of the state and in order to calculate heat and to calculate work and so on. Now, today we are going to consider another diagram which is known as the TS diagram, temperature entropy diagram. Now, entropy is one of the properties of the thermodynamic system which we have introduced previously as a consequence of the second law of thermodynamics. Now, a TS diagram is shown here in this figure, and on this TS diagram for a perfect gas, we will start with perfect gases. TS diagrams actually can be used for perfect gases, and they can also be used for vapors, as we will come and see later on during this class. Now, as you can see on this diagram, the vertical axis gives us the temperature T, and the horizontal axis represents the entropy S. And on this diagram, we can actually plot constant volume lines like the line V1, which passes through the state 1, and we can also plot constant pressure lines like the pressure line P1, which passes also through the state 1, and state 1 is represented by entropy S1 and temperature T1, and the constant volume line V1 passes through 1 and through A, and the constant pressure line B passes through point B and through point 1. And the temperature at A and B are equal, and they are both given by T2. Now, at A we have entropy SA, and at B we have entropy SB. Now, as we can see from this diagram, the constant volume line actually is more steeper than the constant pressure line. Now, this can actually be proved by considering the following analysis. Now, let point A and B be at T2 and V1, that is point A, and point B at T2 and P1 respectively, as shown in the diagram which you have just considered. Now, between 1 and A, from equation 4.8, this is actually the equation which we have developed before as a consequence of the second law of thermodynamics, and by that equation we have shown that the change in entropy SA minus S1 is given by the integral between 1 and A of dq by T. Also, at constant volume for 1 kilogram of gas, we have shown that dq equal CV dt. Now, at constant volume, CV is what we usually refer to as specific heat at constant volume. CV is the specific heat at constant volume, اللي هي الحرارة النوعية عند ثبوت الحجم CV. So if we have a constant volume process, then the change in heat dq is simply given by CV multiplied by dt. Now, we can then substitute in the above equation to obtain SA minus S1 is equal to the integral between 1 and 2. Instead of dq, we substitute CV dt. Then the equation becomes the integral between 1 and A of CV dt divided by T, which is equal to CV ln TA divided by T1. And as we have shown in the diagram above, TA actually equals T2, and therefore SA minus S1 becomes as being equal to CV ln T2 divided by T1. If we consider the constant pressure process for 1 kilogram of gas, then dQ is equal to Cp dt. Cp is what we refer to as specific heat at constant pressure. So SB minus S1 is equal to the integral between 1 and B of Cp dt by T. We substituted for dQ equals Cp dt, and this is equal to Cp ln Tb over T1, which is equal to Cp ln T2 over T1. Now, these two equations, which are in these two squares or rectangles, which are in these two rectangles, we notice that SA minus S1 and SB minus S1 are actually analogous, except for the fact that in SA minus S1 it is a function of CV, and SB minus S1 is a function of CP, and therefore the only difference is that between these two equations is CV and CP. Now, as we have shown before, CP is always higher than CV. يعني الحرارة النوعية عند ثبوت الضغط في العادة بتكون أكبر من الحرارة النوعية عند ثبوت الحجم. وبالتالي, and therefore the equation CB minus C1 is going to be higher than the equation CA minus C1, and this means that point A must therefore lie to the left of point B on the TS diagram, and hence a line of constant pressure slopes less steeply than a line of constant volume, as we have indicated in the previous diagram. Now, in these two figures shown at the bottom here, figure 412A and B, we have a series of constant pressure lines on 412A and a series of constant volume lines at 412B. Now, 412A shows that P6, or we need to identify that, or we need to take into account that P6 is higher than P5, which is higher than P4, which is higher than P3. This means, in this case, as the temperature increases, the pressure also increases from 1 to 6, where P6 is higher than P1. On the other hand, in figure 412B, we can notice that V1 is greater than V2, is greater than V3, is greater than V6, which means as we go along or higher and higher with the temperatures, the volume is going to decrease such that the initial volume at V1 is higher than the final volume at V6. Now let us consider an example using the TS diagram for a perfect gas. The example states that at air at 15 degrees centigrade and 1.05 bar occupies 0.02 cubic meters of volume. Now, these are the first states. This is state 1 in the diagram. We are given the values for state 1, where we are given the temperature in degrees centigrade and the pressure in bar. So this is T1 15 degrees centigrade, P1 1.05 bar, and V1 0.02 cubic meters. This air is heated at constant volume until the pressure is 4.2 bar. That means, as we can see in the diagram, now the constant volume line passes between the points or states 1 and 2. This is the constant volume line, which is the volume in both these points is equal to 0.02 cubic meters. And also on this diagram, we have two constant pressure lines. The pressure line which passes through point 1, which is 1.05 bar pressure, and the pressure line which passes through points 2 and 3 where the pressure is 4.2 bar. Now the air after reaching state 2 at the pressure of 4.2 bar is then cooled at constant pressure back to original temperature between state 2 and state 3. Now it is shown on the diagram. As you can see, at state 3 the temperature is the same as in state 1. So T3 is equal to T1 is equal to 15 degrees centigrade. That is 15 degrees centigrade plus 273, which gives us 288 degrees Kelvin. Now it is required to calculate the net heat flow to or from the air. It is required to find the heat flow either to the system or out of the system or from the system, and the net entropy change. Now when they ask the net entropy change, what is meant is that the entropy change between 1 and 3, because what we are doing is that we have passed through two processes, process 1 to 2 and process 2 to 3, and what is required is to find the change in entropy between 1 and 3, that is S1 minus S3. Also it is required or stated here to sketch the process on a TS diagram. مطلوب أنه نحن نرسم المخطط بتاعنا بالنسبة لهذا المثال على TS diagram. Now, as I always insist on you, please try to draw the sketch whether it is required as part of the solution or not, because as I have told you before, drawing the diagrams always helps you apprehend more or understand more the problem, all the particulars of the problem, and it helps you also to go through and solve the problem correctly. So here it is required actually to sketch the process on a TS diagram. Now we go to the solution. As I have explained to you also many times, please, when you start solving any problem, because in thermodynamics you tend to get lots of data given to you, and extracting the data itself is an art. So try your best first of all to write all the given data before you start in the solution itself. Okay, so you start by given T1 is equal to 15 degrees centigrade, P1 is equal to 1.5 bar, V1 is equal to so on, and you write all the given data, and then you write after that the required. Okay, and then you start in the solution. Now the solution for this problem goes as follows. The processes are shown on a TS diagram in the figure below. From equation 2.64, a perfect gas. Now we have an equation which we termed at that time characteristic gas equation, PV equal MRT. PV equals to MRT. Now this gas equation actually can be rearranged and written as, it applies actually for all states. You can apply it for state 1, state 2, state 3. We are going to rearrange it and apply it for state 1 because at state 1 we have all the properties required to be substituted in this equation and to find the mass of the fluid which is in the system. So rearranging the characteristic gas equation, we have M is equal to PV over RT, or we can say M is equal to P1V1 divided by ROR into T1, which is equal to, now P1 is given as 1.05 bar. I also want to remind you that when you are substituting in equations, please remember to substitute with the basic units of the quantities which you are dealing with. Now, the basic unit of pressure in SI system is Newton per meter square or Pascal. Now, the pressure here is given as 1.05 bar. So you need to convert this pressure from 1.05 bar as a unit into Newton per meter square or Pascal. And to do so, you multiply 1.05 times 10 to the power 5, as we can see in the equation. and V is given by 0.02 cubic meters divided by R for air is 0.287 kilojoule per kilogram Kelvin. We want it in joules, and that is why we multiply by 10 to the power 3, and T must be in degrees Kelvin, and as we have shown on the diagram, it is 15 degrees centigrade plus 273 equals 288 Kelvin. Now, calculating all these particulars, we get 0.0254 kilogram as the mass for the fluid which is in the system. Now, for a perfect gas, also we have shown before from the characteristic gas equation P1V1 equal MRT, we can say P1V1 over P1V1 divided by MRT1 is equal to P2V2 divided by MRT2. Okay, because P1V1 over MRT1 is equal to a constant. So P1V1 over MRT1 is equal to P2V2 over MRT2 is equal to a constant. Now, since we are dealing with the same mass, then the mass will cancel, and since we are dealing with the same fluid, R will also cancel, and we are going to remain with P1V1 over T1 is equal to P2V2 over T2, and at constant volume process, that is between states 1 and state 2 in our diagram, in the first diagram which we dealt with, then V1 cancels with V2, and therefore P1 over T1 is going to be equal to P2 divided by T2. Hence, we can calculate T2 as being equal to 4.2 multiplied by 288 divided by 1.05, which is equal to 1152. So the temperature at state 2 is equal to 1152 kelvins, and at a constant volume we can also calculate the heat using the equation Q equals mCV into T2 minus T1. So the heat transfer during a constant volume process can be calculated as Q equal mCV into T2 minus T1. CV, as we have shown before, is what we refer to as الحرارة النوعية عند ثبوت الحجم, specific heat at constant volume. T2 and T1 are the final and initial temperatures during this process. Now, substituting, we have all the values of these quantities. So M is 0.0254, which you have already calculated, multiplied by CV. CV for air is 0.718, and we multiply that by 1152 minus 288, that is T2 minus T1, and Q1 to 2 is going to be equal to 15.7 kilojoule, and it is heat added because it is having a positive sign. From equation 212 at constant pressure, we can calculate the heat in this case using the equation M into Cp multiplied by the final temperature, which is T3, minus the initial temperature, which is T2. So during the process 2 to 3, the heat being transferred is given by the equation mCp, that is the specific heat at constant pressure, الحرارة النوعية عند ثبوت الضغط, multiplied by T3 درجة الحرارة عند النقطة 3 minus درجة الحرارة عند النقطة 2. We substitute for M 0.0254, Cp for air is 1.005, and multiply that by T3, which is equal to T1 288 minus T2, which is 1152. Now we calculate these numbers together and we get Q2 to 3 من state 2 إلى state 3, Q is equal to minus 22.05. The negative sign, of course, indicates rejection, heat rejection. Now, the net heat flow can therefore be calculated from the equation Q1 to 2 plus Q2 to 3. Now, Q1 to 2 is 15.7, Q2 to 3 is minus 22.05, So 15.75 minus 22.05 is equal to 6.3 kilojoule with a negative sign. The negative sign indicating that the heat is being rejected. So the net heat flow during the whole the two processes, that is process 1 to 2 and 2 to 3, is a heat being rejected, which is equal to 6.3 kilojoules. Now the change in entropy between 1 and 3, this is what is actually requested to be calculated in this example. The net entropy is given by, from state 1 to state 3 is going to be S1 minus S3. So S1 minus S3 gives us the net entropy change during these two processes, process 1 to 2 and 2 to 3. Now from the diagram, we can see that S1 minus S3 can actually be calculated as S2 minus S3 minus S2 minus S1. So at constant pressure, dq equal mcp dt, as we have shown earlier on. Hence, using equation 4.8, which you have developed from the second law of thermodynamics in our previous classes, we can say m into S2 minus S3 is equal to the integral T3 to T2 multiplied by mcp dt by t. Now m is 0.0254, Cp for air is 1.005, ln T2 over T3, which is equal to T1. So ln 1152 divided by 288, and this gives us the entropy change between 2 to 3 as being equal to 0.0354 kilojoule Kelvin. Now at the constant volume process, dq is equal to mcv dt, also carrying analysis similar to those which you have carried above for the constant pressure process. M into S2 minus S1 is equal to the integral between T1 and T2 of mcv dt upon T, which is equal to 0.0254 times 0.718, which is Cv for air, 0.718, ln 1152 divided by 288, and this is going to give us a value of 0.0253 kilojoule per Kelvin, not per kilogram. This should be per Kelvin, just as in the previous one. This is a typing error. Now, therefore, m into S1 minus S3 from the equation on the first line of this slide is simply equal to, as we said, S2 minus S3 times m. S2 minus S3, as we have just calculated, is 0.0354 minus S2 minus S1 times m, which is equal to 0.0253, and the result is 0.0101 kilojoule per Kelvin, and that means the decrease in entropy of air in going these two processes, 1 to 2 and 2 to 3, is equal to 0.0101 kilojoule Kelvin. Now we move on to applying the TS diagram for vapors. Now this is the general shape of a TS diagram which is used for vapors. Actually, it applies for all vapors, whether you are talking about steam or vapors of other substances. It all looks almost the same. It looks alike, just like this shape. Now, in this diagram, as we have said, we are dealing with a TS diagram. The temperature is shown on the vertical axis, T, and the horizontal axis shows us the entropy, S. Now, here we have a number of lines which we need to look carefully. Now, this thick line, which goes up to the peak here, this peak is called the critical point. Now the line which is sloping on this side, on the left hand side, is known as the saturated liquid line. So to the left of this line we have liquid state. The substance is in the liquid state. Now from the critical point sloping down on the right side, we have what is known as the saturated vapor line, or the dry saturated vapor line. Now to the right of this line we have what we call superheated substance. Now in between these two slopes we have what we refer to as wet liquid. Now the substance here is what we call wet substance, okay? And here it is liquid. Here it is a mixture of liquid and gas in this region, and here it is in the gaseous form, or a dry saturated vapor fluid. Now we notice that we have drawn here three pressure lines, P1, P2, and P3. Now this line A, B, C, D represents a constant pressure line on a TS diagram for vapors. A, B, C, D is a constant pressure P1, E, F, G, H is a constant pressure P2, and J, K, L, M is a constant pressure P3. Now the temperature within the wet region here is constant. It coincides with this line, so this is a constant temperature, if you like, T3, and this line is a constant temperature T2, and this line is a constant temperature P2, yeah, and this line is a constant temperature P1. Now the pressure lines, when you go out from the wet region, they actually curve upwards. So this is the pressure line P1, P2, and P3, and as we have indicated earlier on, the pressures are going to increase in that direction. Now also we can draw constant volume line on the TS diagram. As you can see here, it looks like a concave shape inside the wet region, and as you go out in the superheated region, it starts to curve upwards. Now this means we have 5 different regions which we can always deal with: the wet, superheated, the liquid, the superheated, and the wet region, and the 2 saturation lines, saturated liquid line and the saturated vapor line. Now, as we have just stated on the TS diagram, which we have seen earlier on, we have 3 pressure lines, P1, P2, and P3, which are shown by A, B, C, D, E, F, G, H, J, K, L, M, and the pressure lines in the liquid region are practically coincident with the saturated liquid line. Now, in many cases, we actually assume in the liquid region that the property is the same as the property of the saturated liquid line at that particular pressure. Now, portions A, B, E, F, and J, K, those are the portions in the liquid line, and the difference is usually negligible, especially in the cases like the volume and so on. Now, the pressure remains constant with temperature when the latent heat is added. Now, in this region here, when we start heating, say from state A to state B, the temperature starts to increase. As you can see, it is a slight increment from point A to point B, and here from point E to point F, and here from point J to point K. But as we enter in the wet region here, we have what we call latent heat of evaporation. Now, what is happening is that we are adding heat but without increasing the temperature. Now the temperature at point B and point C are equal, temperature F and G are equal, temperatures K and L are equal, and that means you are adding heat but without increasing the temperature. This is usually referred to as the latent heat of evaporation, and during all this heat which you are supplying to the water is being consumed in order to change the phase of the fluid from a fully liquid phase to a fully vapor phase or dry phase at C, for this from B to C, and from F to G, from being liquid at F to being gaseous or fully vapor at G, and from being liquid at K to being vapor at L at a pressure P3. So this region is the region for what we refer to as latent heat of evaporation. Now, the pressure lines curve upwards as we have shown earlier on as we go out in the superheat region, and the portions CD, GH, and LM represent the pressure lines in the superheat region curving up. Thus the temperature rises as heating continues at constant pressure. There is one constant volume line have been shown on this diagram, and the line is shown broken or dotted line, and the line, as I have said earlier on, it has a concave shape down inside the wet region, and as you go out it slopes up more steeply than the pressure line. Now, properties of vapors are actually obtained using what we refer to as steam tables or tables of properties for substances. Now, if we considered one property, now this actually what we are going to say about this property applies for all the other properties which we are dealing with for vapors. If you consider the entropy, for instance, of a saturated liquid and the dry saturated vapor, these two are usually represented by SF and SG respectively. So for saturated liquid, the entropy is given the suffix F, SF, and for saturated vapor, the entropy is given suffix G and it becomes SG. Now this is true for all the other properties. For internal energy, we write it UF and UG. UF as the internal energy for saturated liquid, UG is the internal energy for saturated vapor, and also we talk about HF and HG. HF is the saturated liquid enthalpy, and HG is the saturated vapor enthalpy. Now also we can say the same thing for specific volume, VG and VF. Now, for the entropy, the difference Sg minus Sf, that is the entropy of the saturated vapor minus the entropy of the saturated liquid, is written as being equal to Sfg. So when you go to tables of properties and you find the symbol Sfg, this means this is the difference between the entropy at point G, that is the saturated vapor, and the entropy at F, that is the saturated liquid. The difference between these two is given by Sfg. Now, F's and G's and FG's are all tabulated in the tables of properties. So when you go to tables of properties, you will find at any given temperature and pressure, for instance, you will find values for SF, values for SG, and values for SFG. Now, the problem comes when we are talking about the wet region. In the wet region, in the saturated lines is okay, but in the other three regions, in the liquid region, in the wet region, and the superheated region. Now, when you talk about the wet region, the liquid region, usually approximations are being carried as we have shown earlier on, because the properties along the lines of constant pressure are almost the same as the properties at the saturated liquid line. So we can solve the problem by such an approximation. But when you come into the wet region, actually what you are saying is that during the wet region we have a mixture of the substance. Part of the substance have been converted into vapor and part is still in the liquid state. So the entropy of the wet steam is given by the entropy of water in the mixture plus the entropy of the dry stream or dry steam in the mixture. Now, how can you find the ratio of the dry steam and the ratio of the liquid, the water in this mixture? Now, to find this, we use a factor known as dryness fraction. Dryness fraction. كسر الجفاف. كسر الجفاف أو dryness fraction X. So, what we can say is that at any point within the wet region, the entropy is equal to 1 minus X SF plus X SG, because Sg of the part or X of the part has reached the dry saturated vapor, which has an entropy Sg, and 1 minus X of the substance, a quantity 1 minus X of the substance, or a fraction 1 minus X of the substance, is still in the water form and its entropy is SF. So S at any given point within the wet region is simply given by 1 minus X multiplied by SF plus X multiplied by Sg. We can rearrange this equation and say it is equal, S is equal to SF plus X into Sg minus SF, which is equal to SF plus X into SFG, as we have shown earlier on that Sg minus SF is simply given or written as SFG. Now, this applies also for other properties. So the enthalpy at any point in the wet region, H, can be written as being equal to HF plus X into HFG. The internal energy at any given point within the wet region can be written as U equal to UF plus X into UFG. The specific volume at any point within the wet region can also be written as UV equals VF plus X VFG. Now, X can be calculated from the following equation if it's not given in a problem, or if you have any design problem and you don't have the value of X, then you can actually calculate it by using this relationship here, which is actually generated from the above relationship. So X is equal to S minus SF divided by SFG. X is equal to S minus SF divided by SFG. It is also equal to H minus HF divided by HFG. It is equal to U minus UF divided by UFG. It is equal to V minus VF divided by VFG. Although in the case of V, we sometimes do some approximations, which we will see later on, inshallah. Now let us consider an example on applying TS diagram for vapor substances. Now if we have 1 kilogram of steam at 7 bar and having an entropy of 6.5 kilojoule per kilogram Kelvin, so this is state 1. Our state 1, we have a mass of steam of 1 kilogram having a pressure of 7 bar and an entropy of 6.5 kilojoules per kilogram Kelvin. Now, this amount of steam is heated reversibly at constant pressure until the temperature is 250 degrees centigrade. Now, we are heating it at constant pressure until we reach a temperature of 250, starting from a particular temperature which is corresponding to a pressure of 7 bar and an entropy of 6.5 kilojoule per kilogram Kelvin. It is required to calculate the heat supplied, whether it is heat added or heat rejected, or it's heating, so it is heat supplied, and show on a TS diagram the area which represents the heat flow. Now, as I said before, first of all, remember always to put the given data. So the given data here is that P1 equals 7 bar, SG is equal to 6.709. Now, at 7 bar, when you go to the steam tables or the tables of properties, you will find, or you can find at a pressure of 7 bar, what is the saturated vapor entropy and what is the liquid entropy. You can find all those values from the table at 7 bar. Now, from the table then at 7 bar, we obtained Sg as being equal to 6.709 kilojoule per kilogram Kelvin. Now, let us compare this value with the value of entropy which is given to us. It is known to us that the entropy at this 7 bar of the steam which we are dealing with is 6.5 kilojoule per kilogram Kelvin. But at 7 bar, the table tells us that the dry saturated vapor entropy is equal to 6.709, which is higher than the entropy of our steam, the 6.5 kilojoule per kilogram Kelvin. Now, this means the steam which we are dealing with is actually a wet steam because it has not reached the dry saturated vapor line. Otherwise, its entropy would have been 6.709 or higher. If the entropy is higher than that at that pressure, then that means we are outside the wet region. But since the entropy of the fluid is 6.5 and the dry saturated entropy at this 7 bar pressure is 6.709, then we can say that the steam is actually wet. It's a wet steam. Now, for wet steam, we need to find X in order to be able to calculate the properties. Now, because it's not given in the equation here, in the question here, so to calculate it, we will use the equation which you have generated earlier on, which says X is equal to S minus SF divided by SFG. So at this first state, that is state 1, we can say X1 is equal to S1 minus SF1 divided by SFG1. We substitute for S1, that is the 6.5, the given entropy, minus SF1, we obtain it from the tables at a pressure of 7 bar, which is given by 1.992, and SFG, that is FSG minus SF, we also obtain it from the tables of properties at 7 bar, and it is given by the value 4.717. When we calculate, we get X1 as being equal to 0.955. Now, H1 can then be calculated from the equation analogous to the equation of S1 as we have shown in the previous slide. H1 is equal to HF1 plus X1 HFG1. H, as we have indicated previously, is what we refer to as the enthalpy. So H1, the enthalpy at state 1 is equal to the enthalpy of the saturated liquid at 1, that is at the 7 bar, plus X1, the dryness fraction, multiplied by the difference of enthalpy between Hg and Hf at state 1, that is at the 7 bar. Now, again, we go to the tables and we find Hf1 as being equal to 697 at 7 bar, and at 7 bar HFG1 is equal to 2067. We multiply that by X1, and the final result of H1 becomes 697 plus 1975, which is equal to 2672 kilojoule per kilogram. At state 2, the steam is at 250 degrees centigrade at 7 bar. Now, this actually need to be considered very carefully. When he gives you that at this pressure you have a certain temperature, you cannot assume that the steam is still in the wet region, or it is on the dry saturated line, or in the superheat region. You have to find that out. Now, how to find that out? We go to the tables. Now, I have obtained the table here, or part of the steam table from the superheat tables. As you can see, this part which I have snapped is for a 7 bar, pressure is 7 bar. Now at 7 bar, what is written between these two brackets is the saturation temperature. Now at 7 bar, the saturation temperature is 165, and we notice here that we have actually reached a pressure of, or a temperature, sorry, of 250 degrees centigrade at this 7 bar, which means we have passed, or we are beyond the saturation pressure, the saturation temperature at this 7 bar, which means we are in the superheated region. So the state 2 actually is in the superheat region. We have added heat, or we have heated our steam from the wet region. It reached the dry saturated vapor line, and now it is in the superheated region. Now, from the tables here, this same part which we have snapped from the steam tables, or the tables of properties, we can notice here that we have the pressure, and for that pressure we have values of V, U, H, and S, that is specific volume, internal energy, enthalpy, and entropy for different temperatures in the superheat region. Now, for this part, this starts from 200, 250, 300, 350, and so on. So for 250, the enthalpy for the 7 bar in the superheat region is equal to this value, that is 2955, as is written here. So H2 then, the enthalpy at state 2 is equal to 2955 kilojoule per kilograms. Now at constant pressure, here is the diagram actually. This is the TS diagram, which depicts the problem which you are dealing with. Now, as we can see, we started with state 1, where the entropy is S.5 and the pressure, the entropy S is 6.5 and the pressure is 7 bars, and we heat it until we reached the saturated, the dry saturated line, and then we continued heating until we reached state 2 at constant pressure of 7 bar. At saturated liquid line, the saturated entropy is 6.709, as we have shown earlier on. Now, at constant pressure, Q is equal to H2 minus H1, that is enthalpy at 2 minus enthalpy at 1, which is equal to enthalpy 2 is 2955, as we have just obtained from the superheat tables, and H1 is equal to 2672, as we have calculated using the tables earlier on, and subtracting these two from one another gives us 283 kilojoules per kilogram. And since it is positive, then it means heat added, or heat supplied. And that is obvious, of course, because what we have said in the problem, we are heating. So we are supplying heat, which is equivalent to 283 kilojoules per kilogram. Now the TS diagram is shown here, as we have just explained, and this TS diagram or the area under the TS diagram between states 1 and 2 represents the heat flow as we have shown in our previous study. Now, thank you very much. This brings us to the end of this lecture. See you next time, inshallah.